right, let's start. So today we'll be very happy that we have Cristobal Petrovich giving a talk. Cristobal started his career in Chile, where he's also from, in fact, more south, where it's always windy and cold, apparently. And after Chile, he moved on to Princeton, where he started his graduate degree, and he will be finishing his thesis under supervision of Scott Remain at the IAS and Roman Rafikov at Princeton. So, and then after he graduates, which we all assume is going to happen, he will actually come to CITA starting this September. All right, go ahead.
Okay, thank you, Dan. It's a pleasure to be here and meet some of my future colleagues and future institutions. So yeah, this is a work that I've been doing for my thesis with Scott Tremaine at the Institute for Advanced Study, my advisor, and Roman Rafikov at Princeton. This is a brief outline what I've been talking about. I'm going to start by introducing, motivating the problem, the puzzle of how hot Jupiters or warm Jupiters closing big gas giant planets form, different alternatives. What do we know from observations? How can we actually constrain these two competing scenarios that I'll be talking about? And finally, discuss the alternatives that I've been studying, namely planet-planet interactions, strong scattering, or secular processes that I'll be discussing to conclude with some remarks. So, well, this is not, this is fine, sorry. The hot Jupiters has been a puzzle since they were discovered. It's on top of this, but supposedly, so the first planet that was discovered in a main sequence star was a hot Jupiter. So this is 51 Pegasi b. It was in a 4-day orbit. Here is the RV signal, the rate of velocity. It's a clear sinusoid. And it's been a problem since then because we believe that these planets shouldn't have formed there because first, it's actually too hot, close to like 3-day orbits. So it's hard from the core accretion scenario to accrete an envelope, or for the gravitational instability scenario to actually become gravitationally stable. And it's also these orbital separations, and there is very little mass. So most likely, and this is what most people believe, they form beyond what is called the snow ice line, where icy dust grains can agglomerate in the core accretion scenario, form there, and then migrate inwards. The island is, the snow line is roughly at a few astronomical units, say. So the puzzle now, the question is, how did hot Jupiters migrate? This is a plot showing the exoplanets that have been discovered. This is separation. This is the planet mass. And the color coding is different techniques. So in red here, you have the space-based from Kepler that is mostly discovering low-mass planets. And most of the population of the hot Jupiters or warm Jupiters are going to be in this region where transit ground-based surveys are discovering these hot Jupiters. And this is vaguely defined, but roughly hot Jupiter is going to be something that is within 0.1 astronomical unit. And a warm Jupiter is something in between what I would be calling cold Jupiter. So this population, that is most of the Jupiter-like planets, lining here in these blue squares detected by radial velocities. So something in between, vaguely defined, is going to be a warm Jupiter. Okay, that was unexpected. So the question again, how did Jupiters migrate from, say, beyond 1 astronomical unit to very short distance from the host star? There are two competing scenarios. You need to remove a lot of angular momentum from the planetary orbit. So you can do that by either having these planic interactions. This has been proposed in the 80s. And the idea is that the planet in the disk exchange angular momentum by launching density waves, like in this cartoon here. This is from a hydro simulation. So they have torques, they exert torques with the density waves, and the planet can move either inwards or outwards. In most cases, it does inwards. And the scenario that I'll be talking about is called high eccentricity migration. So some process that I'll be discussing excites the planets eccentricity to very high values. Once the planet gets very close to the star, like in this cartoon here, so this is a planet that is migrating, tides raise, in most cases, in the planet, circularizes the orbit, and the planet migrates inwards. So here you have a sort of cartoon. You have a very elongated orbit. It has very close approaches to the star, and tides can actually drain orbital energy, and the planet can circularize its orbit and become a hot Jupiter. So this process could be many things. Could be planet-planet interactions. This has been discussed by several authors already, Nagasawa, Naos, Janshin, Gu, and some others. I also have some work that I'm going to be showing. And also you can excite eccentricities by having what is called the Kosailidov mechanism in stellar binaries. It's also been studied here locally at CITA by Norm and Janshin and some others, or some other process. So all my studies mostly focus in this part, like planet-planet interactions. So some general predictions this is a fast-moving field, so many of these are still up to debate, but just to sort of have a rough idea of what each of these scenarios actually predict in the simplest formulation. So from this planet interaction, we expect to see planets that have been to be captured in orbital mid-motion resonances. From the high eccentricity migration, so I'm going to be discussing each orbital element. From the high eccentricity migration scenario, you expect the planets to be closing planets to have a perturber, something that actually excited the eccentricities. So a long period companion, but not really close companions. That's mostly because if you have a very elongated orbit and the planet is migrating, anything that is in between this ellipse is going to be orbit crossing. So you expect to eject anything that is inside or actually quench the migration process. From the eccentricities, we expect from this migration to have low eccentricities in general. They tend to damp the eccentricities. From high eccentricity migration, we expect to have a whole population of eccentric planets, and some of them actually are expected to be with eccentricities up to unity. For the inclinations, the last orbital element I'm going to be discussing, migration in this scenario happens essentially in the same disk. So if the spin-orbit axis is aligned with our orbital angular momentum of the disk, you expect to have low spin-orbit angles. From high eccentricity migration, you actually expect the opposite. So this is a cartoon showing, so this is the spin of the host star. I'm going to determine this obliquity, stellar obliquity, or spin-orbit angles, or misalignment angle. And this is the orbit of the planet, so it's this angle actually here. From high eccentricity migration, you normally excite both the eccentricity and the inclination, so you expect to have large spin-orbit angles. As I said, some of these are still up to debate, but you're going to start using the data to actually try to constrain these two migration scenarios. Right, so what are the clues from these orbital architectures in terms of the orbital elements? This is showing the population, again, on mostly RV planets, radial velocity planets. This is the semi-mirror axis, this is the eccentricity. And again, you see the population here of hot Jupiters, warm Jupiters, and cold Jupiters. So first of all, these are eccentric, many of them. Some of them are also in a low eccentricity orbits. So the first problem here with high eccentricity migration that you see is that if a planet is actually in the process of migrating, becoming a hot Jupiter, they need to get really close to the star. And you see that many of these warm Jupiters have low eccentricities. So you can compute the pericenter distance of many of them. And these are roughly, most of them are beyond roughly 20 solar radii, where tide is actually really inefficient. So how do you form these planets by high eccentricity migration? That's something they're going to be discussing as well. If you try to constrain the theories, you can define something like migration efficiency. So this is taking a histogram for the radial velocity planets in semi-mirror axis. So what you see is that there is a large population of planets beyond 1 astronomical unit. There is a pileup there. This is real. You have what is called here the period valley, and you have this population of hot Jupiters. right? So anything that is making these planets migrate from here to here has some efficiency that is not too high, not too low either. So if you compute the ratio between hot Jupiters and cold Jupiters, you get something like this value, like taking the ratio of this and this number, right? So the efficiency is roughly several percent. Now, if you look at the spin-orbit angles, again, this is from the Rossiter-McLaughlin effect. You can measure the angle between the spin, the whole star spin axis, and the normal to the orbital plane of the planet by what is called the Rossiter-McLaughlin effect, where you see that the planet that is transiting, you can measure the radial velocity signal, and you're going to have features associated with the fact that the star is rotating. So this part is approaching us, this part is receding. So there's going to be an excess of red light and blue light in the RV signal. So you can account for the angle. However, it's the projected angle. It's the projected spin-orbit angle has several synonyms, but it's stereo obliquity, misalignment angle, this value of alpha, because you don't know the angle of the spin-orbit axis along the plane of sky. Right, so if you take a histogram, this is being measured for hot Jupiters. This technique is really successful in measuring this, mostly for hot Jupiters. You get this distribution. So you can see that there is a distribution of aligned systems and misaligned systems. These are roughly 60-ish planets. So it's been proposed, this trend was explained first as this population of aligned planets are probably due to this migration, because they don't excite the mutual inclinations, so planets migrate in the disk.
So these are already the hot Jupiters?
These are all hot Jupiters, yeah. This is being measured up to like roughly 0.1 astronomical units. Or, well, there is one planet that is actually this one, that is very eccentric, and it's transiting, and it's in a binary. And it has a spin-orbit angle of like 45, 50-ish. Yeah, so, but most of them are hot Jupiters. Right, so this is the predicted obliquity. And the story in the beginning was, okay, so the planets that are aligned are most likely due to this migration. And there is a sort of like flat distribution of planets that are misaligned. And they probably come from some high eccentricity process like Cosine-Lytton migration or scattering that I will explain later. But from this migration, it's been also discussed recently that in principle you can tilt the disk relative to the spin, the star spin axis, and also be showing that a high eccentricity migration doesn't really imply that the systems are misaligned. You can create this population from high eccentricity migration. And the final clue is to look at the companions, right? So what is the multiplicity? As I said, from high eccentricity migration, we need to have only long period perturbers, not closing ones, because they would be like orbit crossing. So this is showing, again, the same plot. This is the RV sample for the planets that have one planet just discovered and more than one. And when you can compute this to sort of have an idea of what is the fraction of planets that are like hot Jupiters, so within 0.1 astronomical units over the whole population. Here is like 15%. If you do the same for the planets, so this would be roughly like alone, or they have very long period companions. So there are no close companions in this case. If you do the same for the rest of the sample, the ones that have at least one planet, at least two planets, sorry, the fraction is much lower. So that means that planets tend not to have companions, at least close companions. And also, it's been there are campaigns trying to observe if these systems have companions. There is one by a group led by Heather Knudson in Caltech, and they show that roughly 50% of these lonely planets have radial velocity trends. So these are very long period planets, roughly beyond 1 astronomical unit, that are consistent with being planetary companions, not stellar companions. Right, so this sort of fits in the picture of high eccentricity migration. Okay, so to the theory part. So what I'm trying to do here is to explain all this population of planets in a statistical way, trying to come up with a theory that can explain, say, the efficiency, the multiplicity, the orbital elements, semi-mirror axis, eccentricity, inclination, and so on. So the picture is the following. Planets are born in this protoplanetary disk. You start, say, with more than 2 planets. They start with low eccentricities, low inclinations, beyond 1 astronomical unit, roughly speaking. And then the gas disk dissipates. So then you can start exciting the eccentricities, because the gas tend to actually damp the eccentricities. And then the system can become unstable, right? You excite the eccentricities, they can start like orbit crossing, and you start losing planets by, say, ejections or collisions with the star and so on and so forth. And then you heat up the system. So you create some eccentricities, some inclinations from these very cold systems. And then the system becomes long-term stable. So there is a process of dynamical relaxation. And in most cases, this has been studied in many works. In most cases, you end up with 2 planets that are well separated, that are long-term stable, or you can also form a hot Jupiter that it becomes essentially decoupled from the rest of the system. That's another way to stabilize the planetary system. So I'm going to start with this first scenario, that is planet-planet scattering, right? So this is the results from ensembles of planetary systems. An initial state in this simulation, so these are 1,000 systems that are evolved for 20 megayears, including tidal damping and precession from general relativity. We start with 3 planets, low eccentricities, low inclinations, in this range of between 3 and 7 astronomical units, so the system becomes unstable in short time scales. And what you see is this plot over here. So these are the eccentricities. These are the inclinations of all the systems after 20 megayears. And this is the final semi-mirror axis. You have all different outcomes. So planets can collide with each other. Planets can collide with a star. Planets can be ejected, and so on. So you either end up with just 3 planets. So either nothing happened, or one of these became a hot Jupiter. So these are the black circles. You can end up with 2 planets, which is something that happens in most cases. And the most common scenario is to actually eject 1 planet to the interstellar medium. Or you can end up with just 1 planet, right? So this process is giving you a population of hot Jupiters. It's very violent, so it's a scattering. These are close encounters. Planet comes very close to each other, and they scatter to very elliptical orbits, and the planet can migrate. So what you can see, you form this population in 13% of the cases of hot Jupiters that are actually fairly inclined. But also something that is going to be very relevant is that many of the 2-planet systems have high inclinations, as you can see from here. These are values up to like roughly 90 degrees, and are also very eccentric. So if you compare...
Why do they seem to sort of follow on?
Oh, well, you have like this pilot. Yeah. Oh, it's artificial. So the thing is that you're starting with the planets at between 3 and 7 astronomical units. So the innermost is very close to 3. Once you eject 1 planet by conservation of orbital energy, this is going to migrate by a factor of like roughly 2.
I see, okay.
Right, so it's 1 over A equals to 1 over A initial, 1 over A. So
I see, okay.
yeah, but it's artificial, but it doesn't really matter because I'm mostly studying the planets that are inside 1 astronomical unit, the ones that did something. Yeah, that's a good point. Yeah.
It seems like the 1 planet systems are highly eccentric yet non-inclined. Why is that?
Yeah, that's a good question. So in some cases, so you refer to these cases, right? Yeah. So it could also happen that the planets collide with each other or collide with a star. So in principle, I'm not following the spin of the star, but the whole system should conserve angular momentum. So that's probably your question, right? in principle, this is transferring angular momentum to the spin of the star. So then the star would be, the spin axis of the star would be pointing in some other direction to conserve the angular momentum of the whole, right? Yeah. Right, so if you compare this with the data and trying to see if a scenario like this can actually explain the population, at least the hot Jupiters. Here I'm showing the results from the simulation. So this is the semi-major axis distribution. These are from the transit sample, roughly 160 hot Jupiters. And this is from the real velocities. These are roughly 40 hot Jupiters. And you can see that it's totally offset. Actually, the pileup that is roughly at 5% of an AU is not reproduced by these scattering experiments. And what happens is that scattering is really, really violent. So there is nothing limiting getting very, very close to the star. This is like sending billiard balls close to the star. And once the eccentricity gets really high, then tides damp the eccentricities in a very short time scale. So you have a pileup roughly where the planets would be disrupted. Now, if you look at the inclination distribution, you form most of the systems with high mutual inclinations or high inclinations relative to the spin of the star, which doesn't really reproduce the initial plot that I showed with the spin-orbit misalignment angles. So I would say that this scenario, in terms of like failures, is that it doesn't really reproduce the distribution of the semi-major axis. It doesn't reproduce also the fact that there are warm Jupiters in this population. There is nothing. This is empty. And also, there is no aligned distribution for the spin-orbit angles. The success is that it's actually very efficient, I would say. It's probably the only one. So, but the story doesn't end there, because I've been following this for just 20 mega years. These simulations are fairly expensive. So then you end up with this population mostly of two-planet systems that can have high eccentricities and high mutual inclinations. So there are some other processes that can actually happen in very long time scale, secular processes, when the system relaxes. So I'm going to be discussing these two scenarios. And two limiting scenarios is having just two planets that are eccentric, but coplanar, or with low mutual inclinations, or a scenario in which you excite mostly the mutual inclinations, in which case you can have Cauchy-Lederer oscillations that I will explain in a minute. So let's go to the first one. So this is dynamical interactions 2. The second scenario is low mutual inclinations, high eccentricity limit. Right? So the idea that you have to think about here is this is a system that is hierarchical, meaning that the ratio between the semi-major axis of the inner to the outer is a very small value, right? Roughly speaking, it could be 1 astronomical unit and this outer orbit 5 or 10 or 20, right? So what happens in very long time scales is that this process can actually excite excentricities in very long time scales. And the way to think about this is what is called Gauss averaging. So you have to think of this like two rings that are interacting gravitationally, right? And you smear out the mass, for instance, of this ring, the outer body, in this ellipse. And the mass is, in the ring is going to be proportional to the time that they actually spend, for instance, in this part over here. So it's proportional to 1 over the velocity. So if you have a situation like this, the orbits the two rings can exert torques to each other. So let's think about like just the inner orbit. So the inner orbit in this case is going to feel a force going in this direction. So if the two orbits, the two eccentricity vectors, the ones that are pointing to the periapse, are aligned, there is no net torque by symmetry. In this situation, this other limiting situation, you have that, again, the force is going this way, and here is going to feel a maximum torque, right? So actually the torque goes to the cross product of the eccentricity vector of the inner and the outer, or it depends on this angle. So what happens, and something that I discussed in a paper recently, is that you can actually form hot Jupiters by this mechanism. And it happens that sometimes you are in this situation where this angle var pi in minus var pi out, the angle between these eccentricity vectors, can linger around 90 degrees in the situation where you have a maximum torque. It's a sort of like resonant behavior. So you can actually torque the inner orbit, and the eccentricity can grow to very high values. So this is an schematic calculation with a secular code that I wrote, including GR, tidal bulges, tidal dissipation, and following the spin of the star and the planet. So this is a simulation of a planet that actually makes it to form a hot Jupiter. In this case, I'm starting with a planet at 1 astronomical unit and 8 for the outer planet, with relatively low mutual inclinations. Both start with eccentricity of 0.5, and they engage in this long-term process, like secular interaction that can drive the eccentricities to very high values. So the inner one is in black, can go from 0.5 to almost unity, and this can actually repeat in cycles forever, but I'm including tides. So this plot is showing here, again, the evolution for the semi-mirror axis in black and the pericenter distance in gray. So what you see is that you start at 1, but then once the eccentricity gets to very high values in the first cycle, the orbit shrinks a little, right? So here's reaching values of like between 2% to 3% of an astronomical unit, where tides can actually be important. And then the planet migrates and makes it to form a hot Jupiter. Something that is relevant here is that you see that this reaching a minimum value. And the minimum value is because this is a very slow process. So this is happening in mega years. So you have roughly 10 to the 6 orbits to actually grow the eccentricity to unity. And it depends on the orientation of the orbit. So if the orbit is processing fast, then you quench this process. So you can have a process like, I don't know, say GR precession. So if the orbit gets really, really eccentric, and the pericenter gets very close to the star, then GR precession can make these orbits precess fairly quickly, the inner one, and then this whole process actually quenches. So you get to just a maximum eccentricity and a minimum pericenter distance, which is actually something really good to reproduce the data, as I will show next. I decided to call this coplanar high eccentricity migration because it's a process that doesn't really depend on the mutual inclinations. So you can create systems with essentially 0 misalignment angles or mutual inclinations. Here is showing the mutual inclination of the system. It starts at 5, has some moderate excitation, and then this is showing here the spin-orbit angle. So in this case, you form a hot Jupiter with roughly 15 degrees in terms of spin-orbit misalignment angle. So how does it compare with the data? First of all, to compare with the data, I ran this population synthesis. So I start populating. That's going to depend mostly on the initial eccentricities. That's the most relevant parameter. So this is showing just to give you a sense of how things compare with the data. I'm starting with Rayleigh distributions for the eccentricities, an inner planet at roughly 1 astronomical unit, and a perturber in this range. These are the initial values. And here you have the final semi-mirror axis and the final eccentricity of the system. And I stopped the simulations in this case in a uniform time between 0 and 10 gigayears. Like there was sort of like a steady state migration process. So you're observing this not in the final state, but something in between. So you form a population here of hot Jupiters. The red, there is roughly in 3% of the cases in this set of simulations, planets that are migrating, that are in green, and planets that do nothing essentially in terms of migration, that are the black dots. And that's most of the systems. So if you compare, the efficiency here is roughly 3%. If you compare this with the initial value that I quoted, that it was roughly between 3 and 10%, it can actually work in an efficient way that I can actually explain the data. And these simulations predict roughly that 3 to 5% can actually form a hot Jupiter. So it's in a range where it is interesting. Now, if you compare again with the data that we have for the semi-mirror axis and the stellar obliquities, we have the following. Before we had a pileup that it was roughly at 2% of an AU. Now the pileup from the simulation that is in black is roughly at 5% of an AU, and this is because, as I show in the evolution of the system, you have GR precession that is making the orbit not reach extremely high eccentricities or extremely small pericenter distances. So this pileup here is actually real, and it's due to general relativity, because this is a slow process. And you can see from here now that you can actually reproduce at least the bulk of the distribution of these hot Jupiters from the RV sample and the transit sample. Now, if you look at the stellar obliquities, these are in black. In gray is the actual value. In black, you have the values projected for random orientations of the hot star spin axis. And the observations are in red. And what you can see here is that you can reproduce at least the ones that are very hard to reproduce with high eccentricity migration, the ones that are fairly aligned or have relatively low stellar obliquities. And that's again because this mechanism doesn't really excite the neutron inclinations to very high values. So in terms of, to summarize, the successes is that it can reproduce the semi-mirror axis distribution because GR limits the minimum percenter distance. You produce hot Jupiters with relatively low obliquities within 30 degrees, where you have roughly 70% of the sample. And you can reproduce the overall rate of hot Jupiters, so this efficiency. The failures is that it doesn't really reproduce warm Jupiters. You don't populate this region here. And you don't produce the population that are highly misaligned, right?
What are the constraints on the relative masses of the inner and outer planets?
How does it depend?
What are the constraints? I mean, I assume that there's some range that will work and some range that won't.
Yeah. The outer planet has to be more massive. So it's most efficient. So in this case, you see that the inner orbit is also, they are exchanging angular momentum very efficiently. This is going to work even in the test particle approximation where the inner planet is just a test particle. So all the mass and the angular momentum is in the outer one. But it's not going to be as efficient as in this case because they are both exchanging angular momentum. So there is a range. But the short answer is the outer planet has to be more massive.
But how much more massive roughly?
So in phase space, if you think about like the initial phase space, initial eccentricities of the inner and the outer, this is most efficient when the outer orbit has roughly 4 times, 5 times more angular momentum than the inner one. So you have more available phase space. But even in the limit where the outer orbit has all the angular momentum, it can also work, but it's more restrictive. Right, so there is some potential evidence that this is something that is maybe working. So now if you plot, this is again the same picture in a steady state. So this is what you would observe in a steady state for the population of close-in planets, hot Jupiters and the ones that are migrating. Now if you look at the ones that have high eccentricities, so the ones that are in this box, they all have relatively low obliquities. Now if you make a plot for the radial velocity planets, here you have eccentricity and projected obliquity. So if you plot this in this part of phase space, this is focusing on the systems that are close in, so within 0.2 astronomical units, like these planets here. What you observe, there is roughly like a trend, at least there is a sample. So if you take like the ones that are most eccentric, they tend to have actually low obliquities. So at least it's explaining these systems right. And these are systems that are pretty hard to explain otherwise. First of all, because in this migration, it's very unlikely to actually produce close-in planets that are eccentric. So you fail to reproduce the eccentricities of these guys. And also from high eccentricity migration, you can produce the ones that are eccentric, so in this process of like migration, but then the obliquities are going to be high. So this part of phase space is actually constraining, and it's something that the coplanar high eccentricity migration is populating. It would be nice to actually have more data here to see if this is actually consistent with other systems. This brings me to the last scenario. So I talk about having two eccentric orbits. Now you can have the other limit, or even something in between, having two planets with high mutual inclinations, right? So this is something that is being studied 50 years ago or so by Kozai and Lidov in different contexts. So Kozai was studying this in the context of asteroids in the solar system. So here the perturber is actually Jupiter. And Lidov was studying this in the context of artificial Earth satellites. So the perturber is now the sun. And what happens, briefly speaking, is that whenever, at least in this case of the test particle approximation, so again, you have this orbit that is hierarchical in semi-mirror axis. And you have a highly inclined inner orbit. You again orbit average the planetary orbit. And then whenever the angle between the two orbital angular momentum vectors is roughly in this range, you can have excitation of eccentricity and inclination. So they're going to go in opposite signs. And that's been studied for a while already. So I repeat the example. This is very preliminary. So just trying to show you if this is something that can potentially explain the population of warm Jupiters and hot Jupiters. I'm starting here a simulation. Now, instead of having two eccentric planets, I'm fixing the outer planet with an eccentricity of 0.1. At 5 AU, I place the inner planet at 1 astronomical unit. And then you have a random distribution here of both the eccentricity of the inner. So that's why you have all these are the initial states. And the initial inclination relative to the orbital angular momentum vector. And what you have here is the following. Again, here is the steady state picture. So in most cases, the black dots are, again, the ones that don't migrate. The ones in between are the green ones, so the ones that can actually populate, being in the process of migrating. So the ones that are in here, the warm Jupiters. And the ones in red here are the initial conditions for the ones that become a hot Jupiter. So here you have the following. The first good news is that, yes, you produce actually warm Jupiters with low eccentricities. For instance, planet like this. So what happens is that you have this Kozai-Lidov oscillation. So the planet is undergoing eccentricity oscillation. So you can picture one system starting here, and it goes like this. So whenever it goes to a very high value in eccentricity, it migrates by a tiny bit. And then keeps on doing that. So in a steady state, you're going to see this population and haven't really finished migration. So that's why it's important to actually track the steady state picture. And this is being evolved, again, in a uniform time between 0 and 10 gigayears.
So the picture is, it's at a very high eccentricity, and then there's some tidal interaction with the star that reduces its energy, orbital energy. It moves in, and then the oscillation brings it back out to low eccentricity. And I see, so you're predicting that all these low eccentricity warm Jupiters have other planets that are helping them.
That's exactly right, yes. Yeah, so that's the picture. The picture is that there is a perturber somewhere in here, in this case at 5 astronomical units. By the way, these planets have been observed. I mean, there are long period orbits, long period planets, companions to hot Jupiters. There are also these rate velocity trends.
Well, I guess it's true, isn't it, that they won't announce the discovery of a planet unless they have I guess if this can work that right. I mean, so there must be, I mean, think you can test this with, by looking for, noise in the orbital solution that would be indicative of outer planet, even if they didn't have a complete orbit for it.
Yeah, there are several campaigns that are looking into that, and so you have to think that for these radial velocity planets, the time span, I mean, they've been observing them in many cases for 10 years. So they can cover roughly up to like 5 astronomical units. So if they discover, for instance, how Jupiter, they might see just a linear trend if the planet is at, say, 10 astronomical units. Yeah, so that's been a work that is been recently done also by this group at Caltech. There are some other groups also working on that. And there are systems that actually have a companion that they can resolve the whole like sinusoid or the radial velocity signal.
But of course, they don't know the relative information from the
No, no. That's something that might be possible in the future, say with Gaia, right? You can have like the 3-dimensional picture of the planetary system. So it might be possible. That's actually a very good test. Right, so in principle, you form this population, you can. However, I'm still working on this, but the eccentricities tend to look a little bit way too high. And that's going to depend on a few different things, and this is just preliminary. But the exciting thing is that you populate this part of phase space that in the beginning is actually very hard to explain with high eccentricity migration. And also, all these warm Jupiters, the ones that are in here, have relatively high obliquities. So in most cases, it's roughly in 80 degrees or something. That's something that can be tested as well. As for the hot Jupiters that you form by this Cauchy-Lido mechanism, again, given that it's a secular process, then you have GR precession. So it has the same virtues of this coplanar high eccentricity migration scenario. So you reproduce here, this is the simulation, this is combining the RV with a transit sample. And again, you more or less reproduce the pileup of these hot Jupiters, roughly at 5% of NIU. Now, if you look at the stellar obliquities, you have from the simulation the one that is in gray. You project this by having these random orientations of the hot star spin axis. And what you observe is that it's sort of like decaying like this. In most cases, the distribution is like just too wide to explain the whole population. But it's not doing a terrible work, right? So if you compare with the data that is in red. So then in summary, from this scenario, the high inclinations, the successes are that you reproduce the semi-mirror axis distribution, again, due to GR. You produce a population of warm Jupiters. There are somewhat too eccentric, though. And the failures are that the distribution is probably too wide for the spin orbit angles. And the production rate, at least in this set of population synthesis study, is a little bit too low. But that's, of course, going to depend on the, what you assume for the mutual inclinations of the system, which are largely unconstrained so far. OK. So the conclusions are the following. To summarize these the dynamical interactions between planets, I would say the following for the different orbital elements. The semi-mirror axis distribution for the hot Jupiters can only be reproduced with the secular processes, either having high mutual inclinations or high eccentricities, because of the gradual eccentricity growth is limited by GR precession. For the obliquities, well, there is no single mechanism that can actually reproduce the whole population. There might be just a combination of migration processes, as it was proposed before with the scenario of having this migration and high eccentricity migration combined. For the warm Jupiters, only the high inclination case, that is the Cauchy-Lido migration scenario, can actually reproduce this at a reasonable rate and with relatively low eccentricities. And this is a work in progress. For the future, these are a few tests. So at least for the warm Jupiters, there are some space-based missions like Kepler-2 or TESS or Plateau. They're going to be looking for planets around relatively bright stars. So you can actually do measurements of Rossiter-McLaughlin. They're going to discover many warm Jupiters. So that's going to be an interesting test, trying to see if these warm Jupiters are actually highly misaligned or they're aligned, and so on and so forth. As I mentioned, for the mutual inclinations, maybe Gaia can actually disentangle. Now that you have, in some of the systems, you have perturbers, you can ask the question of what is the mutual inclination between them. And maybe with Gaia, you can have the 3D picture of the planetary system. Okay, and I end here. Thank you very much.
Any questions for Cristobal? Can I ask you one question? There was a question. Go ahead.
I don't quite get how Gaia is going to add another dimension. What is qualitatively different when you observe Gaia?
No, well, Gaia is doing astrometry, right? So you're going to see the star moving, right? So it's going to move like this. Right. And you can actually fit the whole 3D orbit in some cases, given trying to fit the motion and the projecting in the sky. And also you have the spectroscopy, so you have the other dimension. Yeah, it's just astrometry.
Any more questions?
How, if Gaia really works according to SPAC, how far out can you make such measurements? How many stars effectively would be good targets?
I'm actually not an expert on this. I know that it's, at least from astrometry, there's been measurements of, at least for gas giant planets, where you will see the star wobble around more dramatically. I mean, there's been constraints on mutual inclinations. One example is Upsilon Andromeda, where the mutual inclination is roughly somewhere in like 40 degrees or 30 degrees. And these are gas giant planets at roughly a fraction of an AU.
That's because basically, the larger the submajor axis, the better,
Yeah.
the larger the wobble. So.
Right.
So that gets better as they get further apart. The radar velocity gets harder.
Yeah, but at least for the
It also gets higher. No, wait a minute. No, the radar velocity goes down.
No. Yeah, but if you take like Upsilon Andromeda as a prototype, that's roughly like a warm Jupiter and something outside. So it might be able to work.
Yes, I'm just wondering, so observations as far as obliquities are concerned show that there's a different distribution of obliquity depending on stellar mass. Right, so higher mass stars have higher obliquity, planets, and so on. How does that work with your model? Do you know?
Yeah, that's a good question, actually. So the trend goes with the stellar mass or the surface temperature being like the hot Jupiters that are in hotter stars tend to have a more random distribution in stellar obliquities. The ones that are in cooler stars tend to have relatively low obliquities. So in this picture, is not being included any dependence on the mass. This is just three-body dynamics plus tides. But some part that is missing here, because in most of the simulations, for instance, in this one, I stop the simulation whenever I form a hot Jupiter, meaning that the eccentricity is low. This is mostly tides on the planet. But if you circularize the orbit, then you can still have tides in the star. So most of the explanations go into that, trying to link. So if you have some previous misalignment, there might be a way to actually damp the mutual inclinations or the spin orbit angles just by having tides in the star. So some of the explanations are that cooler stars tend to damp out the mutual inclinations more efficiently because they have like thicker convective envelopes. There are some other explanations going around. There is nothing. So in this picture, it doesn't really tell you anything. But in principle, you can get the distributions that I quote here and try to, once you form a hot Jupiter, try to ask the question of, given that I have this population of hot Jupiters in this range of 7-meter axis and stellar obliquities, try to see how this evolves depending on the stellar mass. So you can still follow this up. Yeah. So the short answer is not in this picture, but it's a trend that is, there's like too many dimensions to the problem. So you have all these different parts of phase space. Try to actually explain everything at once is kind of complicated.
All right, so that's, thank you, speaker again.